Okay, welcome back from the break. I'll start directly because I'm late. This should have been in the last minutes, but so now you know some basics from solar energy that apply to both PV and CSP, meaning like you know how to position the sun, the power from the sun is like both and the beam diffuse, the difference between them. You have some notion of measurements. I mean, like in terms of power that you can harvest. You have notion of what concentration is or concentration ratio is, what type of CSP technologies are there. You know now that CSP is basically about converting solar energy into heat, and then the heat into anything else if you want to. You know that there are mainly two technologies to do that. Parabolic trough tower technology, both deployed in Morocco today. Now, this comes more into, we start to talk about, I talk about the losses in each. So one of the main losses apply to both and to any other PV system, even though in PV systems are called differently, but one of the main losses is cosine effectiveness, which is how I track, sort of, right? How good do I follow the beam? And then we know for each of them, for trough and for tower, I told you which were the main losses, right? Shadowing, blocking, attenuation, and losses in the troughs, etc. So that's like what you should keep in mind from all this lecture. It's good that we have the air conditioning on again. Thanks. Now I'm going to get more into the commercial side of it. Today in CSP, if you look at the installed capacity, meaning power plants in operation in the world, we have about 6 gigawatt, okay, give or take. About among this 6 gigawatt, 75% of the plants in operation are parabolic troughs, which now you know what it is, like this cylindrical shape, sort of parabolic shape collectors. 25% tower. The other, like the dish and the Fresnel, don't even account for 1%. Like there's literally only like small demonstrations or so on. Out of the projects we have online, more than 70% have storage. And that's of course obvious because back in 2006, PV and CSP had more or less the same cost per dollar per megawatt hour. Like PV saw a rapidly decrease in cost. And then the industry understood that the only reason why we will build anything with CSP is because we have storage. So of course most of the plants then have storage. And if you look at what's being constructed now, so this is what operates today. This is what is being constructed now. So today we are in different sites of the world, soon to commission or starting construction, but already officially granted project, because there's a difference. There are many projects that are under development, which means that there is a plan to have it, but nothing official yet. This 2 gigawatt are already tender, meaning that they have a contract that someone is going to buy the electricity, and they are under construction. And if you look at what's happening today, half and half. I mean, we have on the projects that are being built today, half are tower, half are trough. And all of them have storage. Well, actually, not fully 100% true. There's this power plant in Israel that I don't know why they were able to secure a contract, but they don't have storage. So, but most of them have like 100% almost storage. There's another thing that is interesting about the past of CSP and the future of CSP or whatever, if you put it that way, is that in the past, from 2006 till 2011, when the regulation changed, all of the CSP plants were built in Spain. So Spain is actually like where CSP was, even though the first CSP projects were, the demonstrations were in California, Spain was the one that for the first time, 2006, took the lead and said, we need renewable energy with storage. There was a socialist government back then. They were very supportive with the incentives. They had a feed-in tariff for, if you build a CSP plant with the same characteristics of Andasol, one of the plants I shown, you have a tariff. So many plants were deployed, and that's how CSP went from 0 in 2006 to 2 gigawatt by 2011, only in Spain, because there was this program from the government. We saw the same more or less in the USA. There was like a program that facilitated, there was incentive called, not a feed-in tariff, but a reduction in capex, in investment, through tax benefits for CSP. So that's how CSP like got into these numbers. Like if you look at it all together, it's basically like more than 60% of that. So like most of it came from Spain and the USA. However, since 2011, nothing has been built either in Spain and only few in the USA, the tower ones that I showed before. So if we look at what's happening now, is that the new CSP projects are mainly in what we call like other new markets, emerging markets. So Morocco is one of the leaders into when it comes to CSP because Morocco only decided to go, I mean, the government said, we go for CSP. And that was actually very good for the industry in CSP because the moment when they did that, when Masen was created, and then when in 2010 they launched this plan for NU and so on, happened exactly when they, in 2011, said, we cannot support any of these technologies. We have a recession, we have a crisis. So, and it was like obvious for all industry that like Morocco is kind of like helped CSP survive. Because we had like, Morocco said, well, we need CSP. We need energy with storage and CSP. Before Morocco went for PV, they said, first we build the storage, and then as we have stable energy, we include PV. And that happened the same. I mean, other emerging countries, we have China building a demonstration, but China is so large that for them, a demonstration is like 1 gigawatt, 2 gigawatt, 5 gigawatt, which is enough for another country. But for them, it's like, oh, whatever. Yeah, just like build that there. So, and of course for us, it's like, I mean, 1 gigawatt, it's already a lot. If you look at the whole capacity installed is 6. So China said, let's build 1. And if it goes well, we go 5. So like, if it goes well, actually, China could be, of course, one of the main markets for CSP coming up. But just how you have an idea of what's happening in terms of market. So soon, 2019, we will have probably 8 or so. Now, in the future, looking ahead, parabolic troughs, I mean, despite, now you know that they are less efficient than towers when it comes to concentration ratio and what they can collect and the heat value they can reach, I mean, the temperatures and so on, but they will still be built. I mean, we will still build parabolic troughs. And these are just a number of reasons. I usually like you to tell me why, but one of the main reasons is actually because we have many of them. So because we have many of them, which is what we call here maturity, what they are mature, there are many things that come with it. The more we know now, I mean, there are many companies building components. So this is not something new as it was some years ago. There are companies, industries that sell collectors, that sell the receivers, that sell stuff. They have reached cost reductions and they look into efficiency and so on. Because we have many projects, it's easier to bank or to get debt to build these projects. Because we will get to that after lunch, but one of the main things in these solar plants, it's like, even after you have secured a contract, is who's going to pay for this? Because we're talking about millions of US dollars or well, dirhams or whatever, millions of millions. But because there are many parabolic troughs, now they are easier to bank. I mean, like even commercial banks, I don't know, a bank in Morocco, Atajadi Wafa, whatever the name is, they say they could even go for these banks because now they trust that Nur1 operates well, so it's a business for them to loan. Because we have many, there are cost reductions that come with it. And because we have many, and they're operating since 2006 and so on, I mean, every year, if you look at the production from CSP, even though Spain has no built any more plants since 2011, every year the production from CSP has increased. And it's just because we know how to operate them better. Every year, the operators learn how to start up better, how to ramp down better, how to clean, everything, all this. So of course, we're getting knowledge in that. One key thing, and coming to one of the questions you raised, is that in parabolic troughs, it's not obvious that the field is limited. I mean, it is limited in terms of pumping, because of course, if you have like millions of kilometers, then you need to pump oil or whatever fluid for a lot of millions of kilometers. That's energy, that's consumption. But unlike towers, I mean, like if we remember the picture from the tower, towers are limited in size because after some point, you cannot have more, it makes no sense to have more heliostats because you lose a lot just from attenuation. By the way, this is someone that asked, like, why aren't all the mirrors in front? Here you have, I mean, of course, you can have a system that has all the mirrors in front. This system is in the northern hemisphere, so where is the south? South is there, right? Yeah. So, I mean, we will continue building parabolic troughs. That's the whole point here. There are a number of reasons why. However, if you look at this, I mean, towers, before it was dominated fully by parabolic troughs. If you look what's happening now, we're building more and more towers. And the reason for towers is that the first one is obvious, which is more efficient. So if you have a more efficient system and the system is reaching cost competitiveness, then it makes sense to build that one, right? So higher concentration ratio, we can have, I mean, the reason why it's more efficient is because it's double axis tracked, and because it can reach higher temperatures, so meaning that the power conversion cycle can operate at a higher efficiency also. So from a system perspective, it's more efficient. It is also more secure, because in parabolic troughs, if we are in parabolic troughs, you have this loop kilometers. Like if you look at the picture where we had this, right, kilometers of pipes where you have oil. Oil is flammable. So I mean, this is not something that we publish all the time when we are like reading the news, because no one wants to publish this stuff. But in basically every plant that has been built, there has been a small leakage somewhere in the field that makes us stop the whole production for a day or for as long as it takes for fixing it. Because it's flammable. We cannot just allow to have like, and when you are in these plants, in the new ones, it's being more controlled. But when you are in these plants, it actually smells like oil. I mean, like you are in a location where, in an industrial facility where there is oil pumped everywhere. And oil is flammable. Now, in tower plants, first of all, everything is concentrated here. So it's not in kilometers. And second of all, the fluid that is used in this one is molten salts, which is not flammable. In this one is water, which is non-flammable, of course. So from a safe point of view, that's why towers are also interesting, because they are more controlled. The control of a tower system is easier, both for dispatching, for producing electricity, but also because they are safer. And the last one is, there's a lot of room for innovation. I mean, this is less mature, and less mature also has an advantage, which is like, we know less, so there's a lot to do to increase efficiencies and so on. Here are one of the upcoming plants. In the red ones is the ones I'm working at the moment, and the blue one is the one that is here. So it's going to be, I think, in October. I mean, now it's fully commissioned. I mean, you can see completely constructed. Now it's being commissioned. But the Noor 3 tower is 150 megawatt with 7.5 hours of storage, and that's just like some hours away from you. That's a beautiful power plant. The ones I work with are like basically very similar to this picture I showed before. So this is our plant in Nevada. These other two that we are now soon to start construction, actually start construction in the first quarter of next year. It's Redstone in South Africa and Aurora in South Australia. We have one that it's that was a lot in the news last year. It's the 200 megawatt Diwa, or in Dubai, because it's a low record bid for CSP. And I will go to prices in the next slides, but and we have this, which is this is a beautiful plant, first because the shape of the heliostats is like a flower, but also because this one, it's like, has 17.5 hours of storage at 110 megawatt, which is basically a base load plant, so at all times operating at 110 megawatt. If you look at why CSP will continue being deployed, there are a number of reasons. The main one is technical. And I've been discussing this throughout the day. I mean, the only reason why we have CSP is because we have storage. And the fact that we have storage is not the only reason, but the thing is that we will continue improving our technical part. I mean, that's why we do research in that. So our collector field will get better, our storage technologies will get better, and so will cost decrease along with this. So that's something that's going to happen. Also, one of the main deployers for CSP, and that was actually key for Masen to go for CSP before PV, it's what we call local content. Whenever you build a CSP plant in a region, there is, in terms of job creation and local industry contractor, or this technology is by far 4 or 5 times more than PV, for instance, or wind. Because a lot of the components there are just metallic structures, are just normal engineering that can be sourced locally. Also, this technology requires operators more because of the complexity of the system than PV, for instance. Like literally, in a PV plant of 100 megawatt, you can have 10 people working, including the manager. which is sitting probably outside. But let's say in a CSP plant with 100 megawatt, you have up to 60 people or 100 people working. So in terms of even job creation, there's a difference. So like from a government perspective, this is an interesting technology. It's not only the electricity that comes with it, but the creation of the the ecosystem for the economy, for the local economy. And I have to say, I mean, I've been to Warsaw before the plant, after the first plant, after the second and third now, and you can see the change. I mean, Warsaw and before was only known for Gladiator 1 or whatever, the movie, and some shots, and now it's just like such an interesting town. You have a mix of movie actors, engineers, and these beautiful plants and all this stuff. And you think even something that is actually sad probably it's like before it used to be very, very, very cheap. Now you see how you have many more places that are a bit more expensive. But like you see, like the economy is booming in Warsaw, just because now they're building these plants. And that's part of the reasons why CSP will continue there. And the main one, though, is cost. I mean, like, and you see, this is how different institutes, worldwide known, or even more like financial advisor institutions. So you have first the IEA, it's just this International Energy Agency. So they are a non-for-profit entity for that basically forecasts what's going to happen in 2050, 2060, and even shorter term for each country and so on. So they predict something about how CSP is going to reduce the costs. You have more, I mean, this is the US one, the same as International Energy Agency, but just basically the energy authority of the US, how they see it. You have this is the banks, how they see it. And you have the National Renewable Energy Lab, how they see it in terms of optimistic, realistic, pessimistic or so. And then you have the mid, and if you combine all of them, sort of how if we combine all the different forecasts for cost reductions and so on, how we see it. And what you can see, though, is that, of course, the worst scenario, we have no cost reduction. And that's just not true. I mean, we wait 1 year, we see how the bids react, and the bids happen. And then you see, like, the probably most expected one, which is this black line. So we see, like, so if we're here today, how we are expected to continue decreasing by every year by 10–15% our costs. Of course, there is the possibility that through volume, through mass manufacturing, so I mean like building a lot of, because you're basically building the same heliostat all the time, or the same collector all the time, and so on. So by volume, of course, you can even reach further costs, but there is the potential there. If you compare then, putting all this together, you have different entities. Solar Paces, of course, it's an annex of the International Energy Agency that is only looking at the CSP issues. The Irena is the International Renewable Energy Agency. And what they say, it's like, even if we keep the current policy, meaning like we don't change anything, every country continues developing as it is today, by 2030, we will have something like 20 gigawatt of CSP, 27 gigawatt. If we actually change towards we need, I mean like what is happening today, you know, like CO2 incentives and so on, tariffs, then this could be even like, well, a lot more. Irena does the same. By 2030, we can have 80, they believe, somewhere in between. If the targets or if the policies for carbon footprint are even more aggressive, then it will be even more. But the main takeaway here is then that, yeah, these numbers are far lower than PV. I mean, just think about it. PV today has about 350 gigawatt compared to the 8 of CSP. But CSP, unlike some people thought before, will not die. The more PV, because we will realize we need more CSP, more storage, and storage will continue to decrease the cost, CSP will be needed in the system. And actually, the IEA forecasts that for countries like Morocco and, well, the MENA, the Middle East Northern African region, the share of PV to CSP in terms of installed capacity will be more or less the same, but the share of energy that comes from CSP in a year, because you know, the capacity factor is different. I mean, a CSP plant operates 80% of the time, a PV plant operates only 30% of the time. Then the energy from the CSP in 2050 will be even greater than the PV, and so on. Of course, these are just forecasts. But then I like this picture because this just to show why are all these forecasts. Is that if you look at here, we're comparing CSP in blue, different years. This is just cost. So now we're moving into the cost of it. And then you have optimistic scenarios for PV plus batteries different technologies. I mean, so one that batteries that withstand 15 years, some batteries that withstand 10 years, and so on. And these are very optimistic cost assumptions. And what we know is that at this level, at 9 hours of storage, they are not even close, no matter which forecast you use, to compete. I mean, if you require 9 hours of storage, there is no other option, no matter which type of projection, or if we continue with the experience curve we have, or the projections we have for all of them, that can make them PV better than CSP for such an amount of storage requirements. So it's just like I said. I mean, they are complementary. If you need 5 hours of storage, this picture changes completely, because then PV with batteries in 2030 will be closer to us, to CSP. But that's what the picture, what I wanted you to keep in mind from before. It's like they complement each other. So, and at 9 hours of storage requirements, 10 hours or beyond, CSP is more interesting. Today, by far, no matter which projection, the optimistic one or experience curve or whatever, for PV, you continue be doing so. So we will continue deploying CSP. If you look at how costs have decreased in the past, because of the reasons I've mentioned before, you have here somewhere if you know, the power plant, the Noor power plant, the first one was signed for something like $160 per megawatt hour in 2000, somewhere here. So let's look at this somewhere because Warsasat is somewhere around this. It's between, Warsasat has a 2400, so somewhere around this DNI. And that was 2011 when the first one was signed. So the prices was somewhere around here. What we see from the latest developments of CSP, like biddings everywhere in the world, we see how the red line is for allocation with worse solar resource than the other. That's the only difference. So of course, the better the solar resource, the lower the cost. And DNI stands for direct normal irradiance, which is the beam irradiance. That's what I'm saying. So the better the beam irradiance, the lower you can reach the cost. And what we've seen in the bids is actually even lower than these projections. Like in 2016, I was part of this project, and we bid for $63 per megawatt hour. We lost because the tender was agnostic. So basically, we competed with PV, which makes no sense. But the government only cared about the energy back then, so not when was the energy produced. And the ones, the PV one was something like, I don't know, 20-something, so really, really, really cheap. And this is iconic because this was last year, and this is now the construction started. This was in Dubai. That's what I said. And this is very interesting because the DNI is really bad. It's actually lower than this. So it will be somewhere, according to our projections, will be somewhere around here for cost, but the bid ended up being for 73. Now, when you read all of this, you need to be careful. There's a lot of financial behind this. So the PPA price, or the power purchase agreement price, is not necessarily what we say here, the levelized cost of electricity. And I don't want to get into detail about the project financing, but it's not necessarily the same. It depends on inflation rate, and this is probably what you look at the news, like these values are the first year PPA, the first year price that you get paid for, and that's escalated with inflation, with some contingency factors, and so on. But again, it gives you an indication, this happens for every technology, not only for CSP. It gives you an indication of how prices are lower and lower and where they end up looking at. If you want to compare with PV, again, so we have a project that is it's being built today, CSP that is 73. That's a 2 times tower system with 10 hours storage each. And the latest PV one in Mexico, I believe, was something like, or I don't know if in Mexico actually, but something like $22 per megawatt hour. But again, it's like comparing pears to apples. Like PV produces during the day, produces way less energy in terms of capacity factor. So 100 megawatt plant of PV produces that times, I don't know, if you multiply by 8,760 hours of the day, the hours in the year, sorry, times 30%, which is the usual capacity factor for a PV, compared to the CSP one, which would be like 100 megawatt times 8,760, the hours of the year, times a capacity factor that, depending on the storage, could go up to even 80 or 90%. So it's like, of course, in terms of energy, there's no comparison. And that's why I don't like comparing both of them. But if you want to have a notion, PV will be like 25, CSP is around here today. And now it's to be 11:15, it's only 12, we're just there. So we're gonna talk about the main thing of CSP, which is the thermal energy storage. So hopefully so far you understand the notion of the collector part, but the reason why we have CSP is thermal energy storage. I said it before, so why we will continue deploying CSP? Because we have cost-efficient and reliable storage. It's the only reason why CSP will continue there. This picture is actually nice. It comes back to like one of the questions you were raising. So how much storage do we need? And so this picture is, if you look a whole week for the power grid in Spain, you have in black, this line black, thick black, right? You have the demand for this particular week. For I think this is 7 days, yeah, so for a whole week. You can see clearly, for instance, if you take like, I don't know, let's take, so these are obviously the weekend. So you see how the demand is lower in the weekend. So let's take Tuesday, right? And you see how what we can see from this picture is like where the energy, if the demand was this black line, right? In Spain we have a pool market, meaning that there is a bidding process to get into the grid. So every generator, PV, CSP, coal, wind, nuclear, have to bid, right, in order to sell. So this is how it ends up looking like, the share of. So you see nuclear power plants, coal plants, basically never shutting down because they're not designed to be shut down. So they make sure they bid lower so that they can get into the market. You have the combined cycle plants, which are relying on gas, and basically their bid depends on the gas price every week. And you have the share of PV, which is obvious that it's maximum at solar noon. And it's uncontrollable because it's PV. So the yellow part is the share of energy that comes from PV that day. The share of wind, and the nice thing about wind and PV is that even though they are uncontrollable, if you look at maps like this, they kind of complement each other. The wind maximizes after sunset. So you see how the maximum production from wind comes after the peak of PV or so on, if you look into share. Like the blue starts appearing after the sun or stuff like this. And another thing interesting from this picture is that, I mean, this is the same generation units. So like, it's not that the generation units are like a new plant was built from day 1 to 2. It's the same plants, but you can see how every day, depending on the availability of wind or solar energy, the production comes from different like sources. So you see like Wednesday was clearly a day with a lot of wind. In a power market like this, the price is driven by PV and wind a lot because the price of PV and wind is close to zero. Because what they bid in order to call here is their operational cost. And as I said before, for a PV plant or for a wind plant, you basically have no operation cost. Your labor is like 10 people, and that's it. And if there's sun, you're injecting energy. You don't control it. You just like connect it to the grid. The system is tracking automatically, and you just have the 10 people actually in case something happens. But like, so basically they bid for zero. So everything that is generated from wind and PV gets, I mean, of course, gets to the market because they drive the price down. So that's why there's always no surplus of PV and CSP in the system. Basically what they say is like, the rest we need to compensate with what we call the dispatchable technologies. Meaning the technologies that can provide energy when we want to and how much we want to. So this is uncontrollable, for instance, on Wednesday, but then we still have all this demand to fulfill. So then what we have is a competition with these generation sources. We have our nuclear, coal, combined cycle, and this little the CSP. This is from Spain. So of course, there are way more coal nuclear plants than CSP. That's also why. But it gives you an idea of like, when are these plants needed? Like the CSP is needed the most at these particular peaks you see here in a competitive market like Spain, and when it's actually able to compete with other resources, because CSP is more costly than this too, for instance, but still gets recruited. And there are days where actually, if there is, I mean, you see how well CSP complements with PV to begin with, because CSP can store the whole day, because CSP at this time of the day, in this Thursday, it's just storing energy. You see almost no production from CSP, like very little. And then in the night, you see like the peak of CSP for this. So that's the reasoning behind how much storage do we need? How much so if you look at my market, so this is something for Spain, but in Sweden it will be completely different. We have a completely different mix. We have a completely different profile of demand, etc. So every location is unique, which is also interesting because, of course, otherwise we will have no jobs. I need to design plans for everywhere we go. So knowing that, then my point there is like, when we design a system, it's not only the question of how the nominal power and demand, but also how it's expected to operate. You know, when am I going to sell? When is the energy needed? In some markets, it's obvious. Like CSP so far, it's been getting projects in what we call through what we call competitive bid tenders, which is that the government of Morocco, for instance, in 2011 and then in 2014, said we want a CSP plant. So of course, and then the best CSP plant gets a contract. That's what the government said. There were different developers that then promoted a plant and got the contract. So then, of course, that's a way to promote technologies because then they are not forced to bid in these markets. They have a contract directly with the government. But then the government should understand very well when do they want this CSP plant to operate. So they give a signal, you know, like, we want a CSP plant that should be 3 hours of storage because based on our load and so on, we know that we're going to be needing it like at these times only. For instance. So this is often decided by the system operator, so utilities, the tender, and the role and share of each technology, PV, wind, CSP, and so on, it's basically policy related. It's like it's driven by the policies and by the resources that each country has. There are many stakeholders. One of the main things, though, is that here, one of the great things is that CSP with storage, it's fully controllable and dispatchable. So if you have a good solar resource, meaning anything above 2,000 kilowatt hour per meter square per year, that's just a beam, then you can consider that site for CSP. And then you say, CSP is controllable, it's dispatchable, so let's see what's the role that it can play in my market, in my actual integrated system when I look at all the different generators, the PV, the coal, the nuclear, etc. So because CSP plants with storage are dispatchable and flexible, this is what happens. This is just what we saw in the last picture, same week. But I wanted just to show that, look at first when the irradiation happens. And if you compare radiation with the demand, when the peak demands happens. This is for Spain in the summer. So you see like, it peaks of course at noon. I mean, it would be weird if the solar irradiation is not peaking at solar noon, right? Based on how we defined it before. But the demand is uncontrollable, and you see how it's like acting like this. Now, the demand and the price are often related, but not necessarily true. But you see here the difference in price and demand, with clear peak in the evening as well. So of course, it's more competitive. In a system like this, it's more competitive for me to build a CSP plant that provides energy at the prices where I can, which is higher. And then if you look at the width of this peak, it's like 4 hours. So why would I build a system with 10 hours of storage when I'm only competitive during these 4 hours in the evening? Just to give you an idea. So that's like the reason, the whole behind how to size, how to size both the solar field, the storage, and the power block. That's the things that you're mainly sizing. And again, so you could have let's say, whatever collector field, solar tower, with a large storage unit and a relatively small turbine, 120 megawatt. And then operate for 24 hours if you have a large storage unit. Like, you know, the one I said in Chile. The one in Chile has 110 megawatt with 18 hours storage. That plant will operate something like this all the time, ideally, right? But also, you could have the same storage system and the same in terms of capacity, right, in terms of megawatt hour, and the same collector field, and just change the turbine for a 620, such that then the energy that I'm storing here is enough only to run for 4 hours, because now I have a power unit that requires way more energy. But that gives you an indication. I mean, a system like this then would be probably more suitable for a market like this. So I don't need, and keep these notions. I mean, this tank is the same size, but in terms of hours of nominal power, here it's only 4, and for here it's whatever, 16. But the tank physically, and both the collector and the tank, is the same size. So I'm collecting the same amount of energy from the field and storing the same amount of energy. It's just a matter of how the ratio between the power block, the storage, the solar field. So that's what you need to keep in mind. You can relate them. When people talk about storage, It's good that you keep them in megawatt hour, because then it's really the physical quantity, because hours refers only to this, so how many hours of nominal power I can operate. But and the relationship you can calculate, okay, if the power block needs this amount of thermal power, times the hours gives me the actual energy stored, sort of. Now, there was a question before connected to this, and this is like, then, of course, if you are going to store and you're going to operate a system like this, like 24 hours, then you need to design the field, the collector, the number of heliostats and so on, such that it's large enough so that you can operate and store, right? Because you want to store, you want to operate all the time during the times of sun, but you also want to operate during the times of sun. So then you need to collect way more than what you would need at nominal design point. We usually design for solar noon to operate at nominal point. I mean, at 100 megawatt, 120 megawatt. So then you need to oversize that part of the, like in the tower, the number of heliostats and so on, and that ratio is what we call the solar multiple. Like someone before asked about the solar multiple. So the solar multiple, and forget about this equation, whatever, it's just the ratio between the power that it's required from the power block to operate at the receiver point to operate at nominal conditions. So if a power block, for instance, a power block of 100 megawatt electric has a thermal efficiency, give or take, if it's a steam cycle, of 40%, which means then it requires a thermal power of whatever, you name it, do the math, 100 divided by 40%, 260, whatever. So 260 megawatt thermal. And then you have the efficiency of the receiver, the one that is collecting the heat, right? Which is also, give or take, 80%. So if you divide that, then you have like, to operate the power at the power block at 110, you need, whatever, 320 megawatt thermal of energy from the field. That will be a solar multiple of 1, because only at that point, if I design for that, a solar noon and so on, I will collect 320 megawatt thermal, and then only at that time, I will operate at 110 megawatt electric, because the rest of the times I will not have the energy to do that. So then that's why we play with the size of the field and how I want to operate. Of course, if I increase my solar multiple, I mean, if I collect more than that, basically I will be able to operate more often at 100% load. And then what will happen is also that this extra energy I could store. So that's one of the reasons why you will increase the solar multiple. At the same time, though, you can have solar multiples that are less than 1. Why would you do that? After all these last slides, like if we look at this, for instance, you could do this because you could have a system where you're not interested in having at 12 the nominal capacity, because you're not going to operate at 12. You might only operate here. So basically, all that you collect, you just discharge it immediately here. So you maybe don't need a large system, a solar multiple of 1 system, which is, solar multiple is a notion of this connected to the design point, and we design at noon, so that's why this could happen. You can have a system with 0.5 or below 1 solar multiple. It really depends on what the purpose of the plant is, because it's connected to this size, I mean, to the requirement of thermal power of this size. If then we go to, we know these basic notions, then I want just to keep in mind what are the tests or the thermal energy storage solutions we have today commercially available, because there are many in the research, but like that are commercially available, proven, bankable. We have in all the parabolic troughs, we have this indirect 2 tanks system, where basically the parabolic troughs have oil. The oil is used to heat up salts that are cold at 285 degrees, and then they get hot. I mean, this oil is at 400, so this they go up to 395, 390, depending on the efficiency of the heat exchanger. So then you store them hot. So that's something that we use. It's based on the solar salt, which is just a nitrate-based nitrate potassium salt. The problem with these salts, if we were to say one, it's like that they freeze at 270, so you always need to keep this above 270. And they are stable in the properties only up to 580. So for the case of the trough, it's not a problem because the oil is at 400. But we will see later, in the case of the tower, we could actually reach higher temperatures in tower, but we need to control it because the salts can only reach 580. So that's the 2-tank system. In reality, it looks like this. This is in Morocco. And if I stand up next to it, I'll probably be like here. So these are massive tanks. These are massive tanks. That's why, because they are massive, because they are big, we're talking usually in all the commercial systems, this is at most 50 meters. And the diameter, it's 35 meters or so. There's a limitation on this. The limitation for this comes from the pump. And the pump is placed here, and then it has only a suction pipe, a suction pipe that it has like a length. And the other one is in terms of the diameter, because if we continue increasing the size of the diameter, then we will have recirculation in these parts of the tank, and it will freeze, because I told you already that the salts freeze at 270. So that's why they are limited in size, not just because. So there was a picture I showed before where there were like 6 of them instead of having a very big one. That's because of this that I just mentioned. And here we have the cold and the hot tanks as they were being built. So this is not completely full yet. This is just the insulation thickness. Then they would put another insulation to end up looking like this and so on. And they are very efficient. In terms of efficiency, like I said, if whatever I have stored here on Monday, if I have it full at 580 degrees, and if for any reason we shut down the plant, next Monday it might be at 579. So what I lose is nothing. Again, of course, this efficiency is dynamic. The emptier the tank is, the more you lose, because the more the small amount is exposed to air or to the vacuum. How they look like is like this from an aerial point of view. The main components, then you have the 2 tanks. You have the salt pumps, like I said before. So usually more than one. Like here you have 3. And then you have the heat exchangers. So you have the heat. This is a parabolic trough plant. So you see the trough there. So you have the oil to salt heat exchanger here. If you are a mechanical engineer, you should know why the pipes are like this instead of just doing like this. But since all of you are not mechanical engineers, well, it's because thermal expansion. So every time you design the system like this, you need to consider that these are pipes that are going to be cold, hot, which means that they are going to tend to expand and to contract. So every thermal equipment is built like this in every plant. So it's not just that we were playing around like. This picture happened also during, this is usually not on site, this house, like this White House. What's happening here is that this is an interesting picture. This was when the salts were melted for the first time. So when the salts are being melted for the first time, we do it electrically to make sure that then we can put them all there. Or at least we bring them to 280, because of course they are like, when you buy them, they're solid salts. So we need to make sure that when we start the plant, this is only at the beginning, we have these big furnaces. This is just heating the salts to become liquid. You will not see that in a normal plant. This is just because that was the picture. Now, these are not the only system. This is just the one that is deployed in all 60 plants because of the easiness. It's very easy for anyone to understand this. You just like a liquid that is cold, you make it hot, and you store it hot. And because the insulation of the tank, you don't lose temperature. So it's very easy to understand. But there are many other thermal energy storage concepts. So we can classify them on the way the heat exchange happens. One is, based on that, we have active and passive. So active, for those that are engineers and mechanical engineers, is basically when we have forced convection. So we have a heat exchanger, a fluid to a fluid. So all of these ones are active because we are changing from a fluid to a fluid. We're providing heat. What the difference is between trough and tower is that in towers, it's direct. The molten salts is the same fluid that is the heat transfer fluid. So we don't need these heat exchangers here. And in trough, it's indirect. The heat transfer fluid, the one getting hot with solar energy, is oil, and the storage is salt. So there is this indirect. That's the only difference there. But we also have passive systems. And we can classify them as many. They are actually even more archaic than those because this is something very intuitive. For instance, a passive system is if you have a solid, like a rock, and you leave it outside there, it will get hot. Right? If you leave it outside there for a while, like now now it's sunny, it's probably close to solar noon, it will be hot. The rock, like just the rock or concrete. So of course, if you then pass like any other fluid that is cooler than the rock, the fluid will get that temperature, right? after passing through this rock many times, or for a period of time. So that's basically what passive system is. It's basically a medium that it's like usually a solid material, and they're also called regenerators because of that, because they are hot, and the moment they are in contact with they get hot, and the moment they are in contact with a fluid that is cooler than them, they start to release this energy to the cool fluid. But they are a solid media that does that. And then an example is concrete. You can have a concrete block in which you pass pipes through. A PCM, I don't want to get too much in detail, but it's basically a material. All of this that I've talked before is very intuitive because it's sensible heat. So sensible heat is basically a variation in temperature. Storing because variation in temperature. But we can also store energy in latent heat or thermochemical, chemical heat. So latent heat happens at the same temperature, and it's not so intuitive. But what happens is that if you look at a diagram of enthalpy, power or energy or whatever is connected directly with enthalpy, the moment a solid goes from solid to liquid, or vice versa, the enthalpy peaks. So if you have a media that is doing this transition, you can keep it in that transition and be storing a lot of energy. So we could have a passive system that is just made of this type of media that is transitioning from solid to liquid when it gets hot, and from liquid to solid as it cools down. And that it's like very dense in terms of volume, and it stores a lot of energy. And there we can put there are many things that are used for this. I mean, not commercially yet, but mainly research. But we have salt-based PCMs, so some type of salts that happen to have this transition at the temperatures that we want to. Some types of metallics, so like aluminum, for instance. Aluminum melts at 580. So aluminum is interesting because our steam cycles run at 580, and aluminum melts at 580. So if we were able to design a system where you can have aluminum in a way that during charging, some fluid is getting it hot at 580, and then you pass the cold fluid, it will end up leaving the system at 580 because the aluminum is at 880. Just an example. That's what the PCM is like. And then chemical heat, these are even less developed. I mean, we don't have any commercial system like this. At least for this, we have larger demonstrations, sort of. We're trying to build one in Morocco. We'll see. And this one is even less. But this is basically, there are reactions that are exothermic, endothermic. I don't want to get into much detail, but the thing is that there are reactions that the moment they are exposed to heat, the components of the molecules of the elements of a compound separate. And the moment you put them together, they release heat. So these reactions are interesting because, okay, if I am a CSP industry, I can have such a compound, right, like calcium hydroxide, that if I put heat to it from the solar part of it, then it will create calcium and water and oxygen. And then when I don't have the energy from the sun, if I put these three together, for some reason they will release heat. So that's just interesting, and of course it's a concept that is being focus of research, but we're not there yet. I mean, there's nothing commercial there. So if we had to say commercially available, the molten salts directly, you could also store oil. It's just that we don't do it. I mean, imagine having a massive tank of flammable oil, and then it gets, for any reason, burned. So you don't want to do that. So, but you can store oil. You can store water, molten salts. These are most intuitive. We have the latent heat ones, which again I said it's basically this media that is transitioning from solid to liquid. And then we have these chemistry ones. I'm going to focus in the sensible heat. I mean, this is an example, but because I was asked to. But I mean, sensible heat is the ones we have commercially available. Sensible heat, again, which is storing because of temperature difference. The way we store is like this. For instance, we have in the case of a concrete storage, right? So that is easier to understand. So concrete storage, I don't have a picture. Maybe that's a really bad picture. But basically here, we have blocks of concrete in which through pipes are going. So kind of like this. So you have a block of concrete, and you have pipes. In the pipes, or through the pipes, we have a fluid. So one of the main disadvantages here is that they are one directional. Either you're charging them or you are discharging them. You don't discharge these systems at the same time. But what happens is like, you can have a concrete that is whatever temperature, you can charge it, passing a hot fluid that ends up cool because it gives the heat to the concrete block. Then it's fully charged, right? It's hot. And then if you pass one in the opposite direction, then the heat from the concrete will go to the fluid and then operate until it's fully discharged at the same temperature it was before. So that's the notion for sensible heat systems. It's just that the energy stored is the amount of mass that I have times the heat capacity of this mass, which is actually varying depending on the temperature. So that's why here we have this, and just the difference in temperature. So it's very easy. That's why it's like designing the systems is very intuitive. It's very easy. We usually design them for an amount of heat that I want to store, and for an amount of power that I want during discharge. Here's an example. I don't want to go into much detail on it, but again, the power at time 1, you have it like mass times the enthalpy at temperature 1. The power at 2, this one. Of course, the stored energy is the difference between them. The release one is the difference between them, and you should end up somewhere in another temperature that's close to 1. This is not so obvious because the thing here is that depending on the way this is being discharged, it will not release the heat in the same way. I mean, like, first of all, the very first fluid that passes through will get very hot. But as we continue passing fluid through it and this gets cold, this temperature will start to decrease. And that's why they're called like regenerative. And it's intuitive because then what happens is that the closer to the pipes is getting cooler, but the ones that are given the energy are the ones that are further away, so they will do it at a lower quality and so on. To simplify that, then that's why here in this problem we use like this effectiveness thing, which in reality you don't get. I mean, like, to get that you will need to like characterize a system, like discharge it, charge it many times so that you can come up with an efficiency. But this notion of efficiency doesn't really exist. It's just to simplify the calculations. I like these ones because these are from a real plant that I shouldn't disclose which ones. That's why there's no measurement, there's no where it comes from or anything. But these are data from real plants. So what you see here is that on the upside, this is a tower plant, first of all. On the upper side, what you see is the actual power available. So first of all, in this like red and blue, not easy to differentiate, like these ones, right? Is the expected DNI, so expected irradiance from our equipment and knowledge. So this is what we expect in terms of DNI and what happens. So you see that it's very close to. So we can really forecast today with our equipment what we expect in terms of solar energy. Because we need that, because we need to plan what we're going to do. We're not just waiting for the energy to come to then decide what we do with the energy. We need to know when are we going to dispatch and so on. Then the orange one is the actual power that is collected at the receiver. So you see, like, there's a relationship between the, this is what is given to the receiver from the solar field. So this relationship, of course, it only happens during times of DNI. I mean, you only have the orange during times of DNI, during times of solar irradiance. One thing to keep in mind, though, is that this axis there is a left axis for the red and blue, and there is a right axis for the orange, okay? You just don't know the values here, but the patterns look like this. Now, what you see below is my actual power plant performance based on this. So this is the energy collected. So what I see here on the green one is the energy from the receiver to my hot tank. So the energy that is being stored, or that is, from the receiver to the hot tank. The blue line is my storage tank. It's a percentage of how is it. So you see that every day, in this week of operation, what I did is, what they did, I was not there, is basically every day the plant gets full. You see that sometimes even it's actually full, like it's like a plateau. And then discharge, and then full, and then discharge, and then full, and then discharge. So this plant is clearly designed for a base load operation, like continuous operation. And in this week, it actually managed to do it, and the red line then is the actual power. So you see how this is a CISP plant. On a CISP plant, It's the only solar technology that can guarantee this. This is real data, so the plant was always providing 100% of the load. You cannot do that with PV, with batteries. And this is summer. And you can see it's summer because this is, look at the DNI compared to the hours of no sunlight. So you see like we have a lot of sunlight. And then what happens if we are talking about winter? So of course, the operation in winter is a bit different from the operation in summer. We have here more than 10 days or something like this. We see first how this gets narrower because we have less hours of sun. And we have this, now we have less hours of darkness. Now what you see more often is days that are bad, like this one. You see like here, basically every day was very good. You look at the DNI. Like it's basically no clouds, no time. We have like maximum solar irradiance at solar noon, and then lowering as we go. Sunset, some sunrise to sunset. Here in the winter, we have more clouds, and we have less peak. The peak values hop a bit lower also. Our forecast of the DNI is also worse. I mean, we have a better forecast. If you look at here, we can barely differentiate the blue and the red. In the winter, it's more stochastic. We have less control of what could actually happen. There's haze, there's mist, and so on. The same, we see how, in any case, we know how to forecast it. Some days we do perfect, some days not, and we see like how the plan and what the power comes from the field is, this orange one, what is absorbed by the receiver into the tank, and then how we decided to operate that winter. So the first thing you can check is that we never, in these 10 days, we never had the tank full. Whereas in here, every day we had the tank full. So like every day we were reaching this like flat line. In this winter period, there's no single day where we had our tank full. So what they decided to do in that period of time is like, we don't want to shut down the plant because that requires a lot of process to start up again. So instead of producing at 100% nominal, we will guarantee to produce at lower power during the evening such that at this power level, we know that we're going to kick off again with more energy from the sun and start at 100%. So you see that every day we were producing, varying from 100% during solar time or so on, to in the evening time where we also need less energy. I mean, the market needs less energy. Like this is like midnight. We will have then like, I don't know, operating at 60%, 50% of the load. Are we done already? Lunch? Okay. We'll see. Oh, it's perfect. So is it clear? Like, so you see, like, this is the flexibility of a CSP plan. And you see how it's actually challenging to design, because if you design for a summer point, like a summer day, this is your design conditions, you know, like a lot of solar energy, this is what will happen. If you design for a winter day, this is your design conditions. You have less energy, and then you need to see how you operate it. Of course, anything in between will happen in the equinoxes. But the CSP plan gives you the flexibility to do that. And then you see that even in winter, we could guarantee for most of the high demand hours, all the nominal capacity. We just lower it during the midnight so that we could never shut it down. That's the only reason why we did it. Okay, questions? Let's see. System. What's the name of the website? It's this one, no? Klaxon.
Yeah.
This one.
Okay, that's it.
Okay. Okay, let's see. Hello. Okay. Is the use of CSPs in the industry to produce heat an active solution to increase energy efficiency in this purely energy-consuming sector? Yes, you can use CSP like you saw for the oil industry. I mean, the oil all industry requires steam at some pressure and some temperature levels. The car industry will require steam at some pressure and temperature levels. The food industry can also do, and we can design a collector system that can meet the demands of the car manufacturing, the food producer, etc. So you can have CSP for heat, and you can design a system for that. Since we are talking about storing energy, of course we should mention transport energy. Is there special companies for transporting energies? Do you have any numbers of approximately values of transporting energy? Well, we're not transporting energy, I mean like stored energy here. Of course, here we are the only transport happens between the hot tank to the heat exchanger, which is, you saw in the picture, it's just there. So we don't bring like heat from kilometers here, which is like the heat exchanger is literally next to it. And then used to produce electricity. So what is distributed here is electricity, if you want to put it that way. I mean, like once we generate electricity, it goes into the grid. And then you have transmission losses, the same ones you will have for any other generator. And transmission losses, okay, depends, they go with kilometer distance, and I would be lying if I give you a value, but I know that in most of like regions, like cities are like 200 kilometers away, 100 kilometers away, the efficiency of the transmission of an AC line, it's like above 96%, 95%. So no one really, I mean, you consider it, but it's very high. That's not where it happens most of the losses. Nevertheless, there's still a gap there, so we can make it better. And now what we're seeing for the future, it's like moving into small cities, local generation, and even so that these distances get lower, but also then changing AC lines to DC lines, because DC is highly more efficiently transported than AC. And before it was too costly, now it's no longer that. What is DNI? This is a very key thing that you should remember. DNI is beam irradiation. The thing is that irradiation, it's power per meter square. Irradiance, and this is direct normal irradiance, is energy per meter square. So DNI is basically energy per meter square per year, so that I have a notion. So in a location like Warsaw, the energy per meter square in the full year is using a typical methodological year, because I know I told you, every year is different and so on. In Warsaw, it's about 2,400 kilowatt hour per meter square per year. That's the DNI. In Chile, so one of the projects I work with is the best DNI forever. I mean, like I've seen in a project, and it's 3,600, so 3,600 kilowatt hour per square meter per year. And of course, that has an impact directly on the cost of the system, because you need way less collectors to reach the same thermal power in a location where you have such an amount of energy than the one in other places. It makes no sense, economically speaking, to build a CSP system where the DNI is lower than 2,000, because it starts getting too costly. You need a lot of collectors to reach the power that you need. We still have systems at 1,800, 1,800. Below that, it actually makes no sense, probably. In market energy, there is lobbies, especially in the US, on United like Texas, Nevada, where prices, tax, and PV product were increased highly than people can pay. So civilizations are reducing using PV panels after a while of increased CSP doesn't face this problem. Okay, this is not a question, I guess this is a commenting. I think, first of all, I think there are lobbyists everywhere, not only in the CSP, not only in the US. But, and there are incentives everywhere also, it's just that the incentive mechanisms are different. So yeah, one of the incentives could be tax reductions. Let's say that's something that we see directly as a consumers. And as a consumer, I can put PV, I cannot put CSP, we already know why. I mean, we're talking about different scales. As a normal person. But I mean, for instance, like what we see in Morocco is some sort of an incentive, because in Morocco, there is no full market like I've shown before. I mean, like the generators are not required to bid every day to see if they sell electricity or not. Basically, in Morocco, what happens is that every generator has a contract signed with the ONE, and they have a 25-year contract at a specific price. And they produce only when ONE tells them to do. So ONE controls, like, we know the demand coming, we know that you are there, so you go online at 3, you go online at 4 p.m. So, and that's some sort of incentive for CSP, because even though we're not bidding, I mean, the government said we want CSP. So of course, there's like a demand, there was a request for CSP. So there are different incentives, that's the point there, and in every location they will vary. You have direct incentives like feed-in tariff, you have direct incentives like tax reductions for normal users, and you have these bid systems like Morocco, competitive bids, which are to some degree an incentives. Can energy storage be applied to facilities with a nighttime cooling load? I don't follow the question, but you could store cold energy, you could store heat, like hot energy, high temperature or lower temperature. So even if you require cooling, you could actually have a parallel cooling storage system to store cool energy, if that's what you want. So SM is solar multiple, okay? So that's the ratio of thermal power needed from the receiver at nominal conditions to run the nominal power clock at this nominal size, and you can increase it if you want to include storage and so on. Why we use two tanks with two different materials for storage? They have the same material. We're just passing it from one tank to the other. So it's cold, we heat it, we put it in the other one. So when one is full, the other is empty. When one is half, the other is half. That's what's happening in these plants in terms of media. And the tank, the insulation is the same. It's just that the hot one, of course, has another layer because it's going to be at 580, and the other one is at 280 degrees Celsius. We could have a single tank, or we could have a concrete system, but then again, this is our other type of storage. I didn't understand the concept of the charging and discharging of the sensible heat example. Well, what I wanted to keep from here is like sensible heat, storage can be classified in sensible heat storage, latent heat storage, chemical heat storage, right? The one commercially available and easier to follow is sensible heat because it's basically storing because of temperature difference. So like, it's like you guys go back home today, it's very hot, so you will take water from your, from the sink, whatever, right, or from this one, and put it into the, these block coolers, and put it into the fridge, right? That's storing energy, and that's doing it, well, there is a combination. There you have a sensible and latent heat because it will transition to solid. But what you're doing there is bringing from, the water could be at 30 degrees, right, whatever, when you open the sink, or 20. And you bring it to 0, which is like whatever temperature is on the fridge. All that, even before it becomes a cube, a solid cube, that's storing energy because you put water that was 20 at 0 and you store cool energy. That's what you did. And of course, in our case, we store hot energy, but the notion is the same. You are just cooling or heating. And it's a matter of only the heat capacity of the fluid. So a heat capacity is an intrinsic property of the fluid. You can measure it. So basically, a fluid with a high heat capacity is better for storing. It means that it requires less amount of fluid to store energy from 200 to 100 or whatever. And why the most CSP plant in the world use sensible heat storage? Even the latent heat storage can store more than sensible heat storage system. Well, it's not true that one can store more than the other because it depends on how you size them. But what it is true is that latent systems are more dense. So meaning that per cubic meter, they can store more than per cubic meter of a sensible heat. So on that perspective, it is true. But then the reason comes back to what we were saying before. It's not only the technical issues, it's costs. It's more costly today to put a PCM or a latent heat system. And also, we don't have the know-how yet to build a system. We don't know what will happen in terms of the lifetime, the degradation of this system that is going from liquid to solid all the time. Whereas for the liquid ones, we know. So that's why, that's where the CSP industry is going. Of course, there's a lot of we're moving from steam cycles to gas cycles, hopefully, from sensible heat to latent heat, all of this. But today, it's not there yet. I mean, it's costly. We don't know technically if they are proven, etc. The storage technology most efficient so far, the two tanks. That's why it's deployed. I mean, most cost efficient. Okay, not the same as just technical efficient. The most cost efficient two tanks. Is there a case when the tanks don't, which one has the highest efficiency, sorry? Two tanks or thermocline? It depends on how you define efficiency. But if efficiency is, the whole point of today I have my system at 580. If I don't do nothing in a week, I will have 580 again. This holds true for both, for thermocline and for the two tanks. The problem is that as I start discharging my thermocline, to keep the same power output from it, I will need more and more or less fluid, so that then it's less power that I can, less temperature to power ratio. So like the quality of the output of a thermocline varies in time, depending on how charged it is. Whereas for the two tanks, it's directly like if you have hot fluid, you just deplete it as you want to, and the quality of the output will depend directly from you, not as how much it is charged. Sort of like that. And then if you measure efficiency from that point of view, then the two tanks is more controllable. But you can also learn to control the thermocline. And what will happen is that you will over-design the thermocline a bit. You will add cutting off temperatures for the operation, and so on. So we have 3 more questions here. Is there a case when the tanks don't discharge at night and you end up losing energy the next day? Are there emergency scenarios allowing to deal with this? Well, there's no emergency if you just keep the energy stored there. Like I said before, you can keep it there. It's very well insulated. And actually, in a week, you will probably lose only 1 degree. In 2 weeks, you will imagine 3 degrees and so on. So like you can keep the energy there. Of course, it makes no sense to do that. And there's no an emergency there on that perspective. Of course, if you let the salts reach their freezing point, which is 280, then we have an emergency because they will convert into solid. They will freeze. And then it takes a lot of energy and time to actually melt them again. But that never happens because, of course, you won't let that happening. And the whole system is fully traced. So you have electricity in case you need it to guarantee that they're always above the freezing point. The storage chemical is better than storage sensible heat or latent heat at energy density, but most of the seafood plants use sensible heat. This comes back to the same reason as the latent one. There is no cost-efficient, proven thermochemical storage technology for CSP, or actually for any high temperature. I mean, we just know that theoretically there are reactions that are good, that are endothermic, exothermic, but after, I mean, a reaction that has been proven for a number of years, for a number of cycles, we don't know. And actually, what we do know from the first tests, I mean, that are out there in labs, is that these are actually not as reliable. That the material starts to degrade. That you need. I mean, one thing is theory, and that the reaction acts like this. But another thing is all the equipment, the balance of plant that you need for the reaction to act like this. So that all of this, it adds a complexity, and it's not viable yet. By exploiting CSPs in the industry to generate heat, is not an expensive solution? Yes, it can be. It depends on how you define expensive. I mean, it could be in a place like Morocco where you literally need to import gas or any other fossil fuel. It might be cheaper to use the heat from the sun. In a place where, like Saudi Arabia, where you literally dig a hole and sometimes it just comes liquid, and then it might be cheaper to have an oil burner, right? So it's a matter of where you are and the technology available. It's not obvious that CSP will be more expensive. And actually, in the long run, I mean, this you need to keep in mind. One thing is investment costs. So from an investment point of view, CSP will be more expensive. You need more equipment. You need all of these things to happen. From an OPEX point of view, which is the operational cost, CSP will be way lower expensive than a natural gas or diesel engine because then you need to purchase diesel all the time. That's the main thing. And that will depend on the price of diesel, gas, whatever fuel you have. So it's not obvious that one is cheaper than the other. By exploiting CSP, what is a thermocline? Thermocline is a system like a regenerative system, like I said before, where basically you have you create a thermocline zone, which is like in the same concept, in the same tank, you are charging and discharging, which means that if the tank is fully charged, this big part of it will be hot and only a small part of it will be cold. But then if you consider that this is happening in the same single tank and there are thermomechanical stresses, we're keeping the cold and the hot at the same point, there is an area that we call the thermocline area, which is basically dead energy, dead area, because it's neither hot, neither cool. It's just like a dead area. As you charge or discharge, this dead area, it's moving around your same tank. That's the thermocline zone. That's what we define it. Thank you very much. Thank you. Well, that was just a question, actually, but thank you. What are the most powerful softwares to design a storage system? It depends. This is actually, this is the same for any other mechanical component. You need software for thermal stresses. You need software for fluid dynamic analysis, how the fluid's behaving. You need different software for the material corrosion. So like, it's a combination of, and you need software at system level. Okay. Yeah, so now we're done. Now we go for lunch, right? Yeah, so thank you now.